Joe, we are happy to be here for your PhD defense, and I'm happy to present of your jury. Okay. So you know that you have 45 minutes to present your work, and then continue questions and so on. Please go ahead.
Hello everyone, thank you for coming. So myself, Geo. Today I'll be presenting my PhD thesis on Cheops reloaded further steps in decoupling geo-distribution from the application business logic. My thesis director is Adrian Lebre. The president of the jury is Dalila Tamzalit. The reviewers and examiner are Fabien Boyer, who is with us online, Pierre Sons, and Fabien Baliga. I work with the STACK research team, which is a collaboration between INRIA, IMT Atlantic, and LS Dusan Labs. I welcome all of my colleagues and friends also. In this thesis, I'll be presenting, so the contents will be, I'll start with the context, then I'll present 3 contributions in which I'll explain the first 2 in detail, and the last one I'll be explaining in very short due to the time constraints. And I'll finish the presentation with the conclusion and the future perspective. So let's start with the cloud. A cloud is basically a collection of small, many devices or computing units which we often call as servers, and they collectively create a single platform for processing. In this particular cloud, there consist applications which are often termed as cloud applications. So imagine that we have Netflix. We don't work with Netflix. I'm just using the example of Netflix for easy reference. So imagine that we have 2 Netflix replicated application of Netflix, one in India and one in France. So a user can access these cloud instances or cloud application via the networks. These cloud applications are made of services. For example, if a user requests to play the Dune movie, the request will be sent to a service called as play. This service will contact another service called as video to get the video, and then also contact another service called as audio to get the audio and return the movie back to the user, play the movie back to the user. In a generic way, let's say there is a user who requests for a resource to get the resource A from service A. Service A in turn contacts other services like service B, service C to get other resources B and C to create this A and returns it back to the user. Now, these cloud instances or cloud applications are often placed in a far distance. So there could be high latency due to this between the user and the cloud. There came the edge in the literature in which it reduces the data transfer by being in between both of these cloud and the user, such that user can contact the edge, then edge contact the cloud. But again, the problem here is that there could be frequent disconnections due to the network issues between them, and also the edge is compared to the cloud very has less resources. To address this challenge, an initial solution would be to have a local first software. A local first software is something in which all the resources will be available locally at each and every site. For example, for a request in France, we'll have all the necessary things to play the Dune movie in France. Similarly, the case in India also. So this actually promotes autonomous sites in which each user request is processed independently, and they are able to process the request even during the network partitions. Local first comes with collaborations. For example, if a user requests to play the Dune movie, but imagine that this particular audio which they requested in an Indian language is not available in France. What happens if such a resource is not available locally? In such scenarios, we need a collaboration between 2 different sites such that the service play can contact service audio from India to get the audio and then return or play the Dune movie back to the user. In our initial survey, the existing collaboration approaches we classified into 3. The first one is service to service collaboration. In such a scenario, we have a collaboration between two different services such that the services contact with each other and they create a collaboration between them. But the problem with here is that collaboration code is tangled with the business logic, which makes it intrusive highly. The second one is database collaboration, in which there will be a database which facilitates the collaboration between multiple sites. Here the problem is that resources often have a context which can create side effects. For example, imagine that we have a Dune audio file which is located in France and another one in India. There could be two different parts. For example, in France it could be sound Dune audio. In India it could be audio/Dune audio. If we try to share them, there could be a problem with the particular value of that particular file. The third one is broker-based collaboration, in which we have dedicated brokers which is sitting between services to facilitate such a collaboration. The problem with here is that in the existing literature, brokers need to be developed for each services. This could again, the first two will be too intrusive, and the last one could be very expensive due to the requirement to develop individual brokers. This brought us to the general research question, which is there an approach to geo-distribute any service-based applications without being intrusive to its business logic? We went back to the survey and we noticed the broker approach again. So the broker by default is non-intrusive in nature because it is placed external to the application. But at the same time, it is expensive because a broker needs to be developed for individual application. But can we make this generic? For example, a generic broker for any application that can facilitate collaboration between different sites. Yes, so that's when Cheops was developed. And Cheops aims to geo-distribute any microservice-based applications. Cheops intercepts these user requests and geo-distribute them based on a domain-specific language, which is called as scope lang. And this scope lang was actually proposed in my colleague Mary Delavern's PhD thesis, who's with us online. And it will have just one additional component, which is we have the normal application command, which is, for example, Netflix play Dune, the movie, and the scope side, which tells that take the video from France, take the audio from India, for example. So these two will be combined and we are able to create the geo-distribution layer. With this, we created some collaboration approaches also. First one is sharing. In sharing, we have two different replicated cloud instances of Netflix, which is connected via Cheops. In such a scenario, if a user requests to play the Dune movie, the request is sent like this, in which it's like Netflix play movie Dune with the scope, audio from India and video from France. And Cheops does it exactly as the user says, because it can communicate with the services internal. This has been validated on OpenStack with VM and image resources primarily. The second one is replication, in which when a user tries to insert a Dune Part 2 video, what happens here is that we have the same request again, and we attach the scope in such a way that replicate the video with France and India. So it will go and put the resources in both the sites. This replication has been validated on Kubernetes. But something we observed for replication in general is that imagine that we have two sites, again, France and UK, and we have the audio languages, which is a replicated resource among these two sites. French and English is replicated among both the sites. Imagine that a user wants to add a new language, Spanish, into this particular set of languages. By default, what happens in replication is that it goes to both the sides because we need to ensure the consistency and it goes to both the sides. But is it required really? Because Spanish speakers in UK are comparatively very less to France. So this actually, in some context, could create an unnecessary synchronization across the replicas. So we have the first two collaborations, sharing and replication, which is addressed in my colleague Mary Delavan's PhD thesis. And with this problem, we bring the third collaboration, which is proposed in my PhD thesis, which is cross, in which we share one resource among different sites. So this brings us to the first research question, which is, can we design a collaboration approach that solves replication challenges while following Cheops' local first, non-intrusive, and application agnostic principles? We did a survey, and from the survey, we noticed two major approaches, which is Shard Scheduler, which is a research done by a team from Belgium. Second one is Shard Manager, which is a research done by Meta, the Facebook parent company of Facebook. What they did here is that they geo-distribute the resources into smaller units called as shards. And they place these shards at each and every site as individual resources. For example, we have a resource R, which is split into three different resources like R1, R2, R3, like that. But these approaches are intrusive to the application. What could be done here? Can we envision a non-intrusive approach with sharding that follows the Cheops different principles? We have cross-collaboration. We propose cross-collaboration. We have the original resource, which is the set of audio languages, which is in French and English. We shard the resource based on the region. For example, French will be kept as a single resource in France, and English will be kept as a single resource in UK. This process is called a sharding process, which I'll explain. We not only shard the approach, we also aggregate it back into a single resource for a user request, and the aggregated resource will be equal to the original resource. And this process is called as aggregation. Let's look at the sharding process initially in detail, which is, we have a user request to insert the same language, the Spanish. We put a sharding logic, which is put this language only in places where there is users or speakers greater than 1 million. So we have the original sharded resource, which is English in UK, French in France, audio languages. And we insert Spanish in France because compared to UK, there are significantly higher or greater than 1 million users or speakers in France for Spanish language. How do we define such a logic? Can we do it in a non-intrusive manner? This brought us to the cross logic, which is, we have a user who's sending the initial set of resource, which is the initial set of languages, along with this cross logic. So cross logic is an additional input which is given by the user when a resource needs to be sharded. This is sent to individual sites, and at each site they process and get the necessary values for that site from the original resource. For example, English in UK, French in France. This particular cross logic follows an object-oriented programming paradigm in which we have resource logic, which is very similar to a class. Currently, it is expressed in Golang, and it defines how to extend one resource or how to shard a particular resource. Similarly, we have resource local logic, which is very similar to an object, which is an instantiation of the resource logic for each of the shards. And the value is initiated with an operation and stored only at the assigned sites. For example, in the audio, we have a very simpler code for the particular audio example, in which we define that we need put a thing in which like the speakers are greater than 1 million, and here we put the languages. So this is a very simpler example. If we take a list, there is a problem of ordering the elements. So that becomes a bit more complicated problem to address in this resource logic. So this is addressed in my thesis. But many times, sharding alone may not be sufficient. For example, we have the original resource, which is the French and English audio languages. We attach a name, a metadata called as Dune audio. We say let's say we shard the resource. One option is to shard the name as well, if we are sharding all of the resource. But this could be intrusive because it requires more additional efforts, which is quite unnecessary. And it also requires to change the user request at times. So instead of doing that, what we propose with Cross is that Cross combines sharding when required, other times replicate. The second concept is aggregation, which is coming with the sharding. Let's say we have the two sharded elements, French language and the English language, in two different sites, France and UK. A user sends a read request. Cheops contacts all of the involved sites to get the resource. And at the local site where the initial request was sent, the resource gets aggregated into the single resource and returns back to the user. But what happens if a shard is unavailable? If there is a network disconnection, for example. In such a scenario, we have the partial error concept in aggregation, which is imagine that we have three different sites which are distributed via Cheops. We have a GET request coming from the user. So this site one and this site one is exactly the same. I just put it there for better illustration. So a user contacts site one, Cheops, with a GET request. It forwards the request to each and every site. Each of the Cheops processes the request independently and returns the responses back to the user, individual responses, which is the different responses which is got. And the local Cheops will aggregate these responses and send it as a response back to the user with all of the error codes and success messages, everything which we get. Cross has been validated on Kubernetes. So we initially in Kubernetes, we have a deployment resource, and in a deployment resource, we can define replicas, replica numbers. If we try to replicate such a resource, by default, what happens here is that there will be 3 replicas on site 1, 2 replicas on site 2. Sorry, 3 replicas on site 2, which may not be necessary at all times. But with Cross, what we can do here is that we can specify individually how many replicas or how many part of a resource need to go to one site and how many needs to go to the other site. So for example, we can create a configuration such as this, in which the replica is equal to 1 in site 1, replica will be 2 in site 2 for a deployment resource. This has been validated on the Grid 5000 with 2500 lines of code, and it is available on GitLab. Another one is share latex. Imagine that we need to create share latex. We need to create a project in which we have 2 text files, a.text and b.text in site 1 and c and d in site 2. We can create a project in share latex very similar to this, in which this is considered as a single project, as a single resource, and it can be distributed across different, the file can be distributed across sites. This has been theoretically validated. So, just a moment. We saw the inconsistencies between the geo-distributed resources. especially for the cross collaboration with the particular metadata, the replicated values in a cross collaboration. Second one is replication in Cheops in general. Cheops, sorry. So we need to, if operation comes and updates a local value, it could create an inconsistency in the data if the value is not complete, if the value is not propagated to the other one. Especially, there could be some concurrent conflicts happening. We focus on resolving these concurrent conflicts between operations. So let's say we have a resource called as K, which is replicated across site 1 and site 2. At time t, it's completely synchronized, there is no issue. At time t plus 1, an operation comes, a blue operation, which is propagated to the other site. So no issue again, it's synchronized, no problem. But let's say at time t plus 2, we have two operations which are concurrent, a yellow one and an orange one. In such a scenario, it gets propagated to all sites, and I'm highlighting the point that all operations are local first. So an operation happens locally first, then only it is sent to the remote sites. This will create a synchronization issue because the previous state of the operation will be different when they try to apply it locally at each site. This is called as concurrent operations, which is well defined in the literature. And the existing Cheops consistency approach proposed in Mary Delavan's PhD thesis is a raft-based approach with a resource state rollback. I'll explain about that in a moment with this. The existing widely used approaches are, first one is the consensus based, in which we have a raft, Paxos, etc. Second one is CRDT based, which is the different CRDT approaches which are there, like auto merge, operation CRDT, etc. Consensus based are not local first in general, but they are non-intrusive because they can be done external to the application. CRDT are local first, but they are intrusive because they need to create individual data types for the particular synchronization. Then in my colleague Mary Delavan's PhD proposal, she proposed a raft with a rollback, which is initially when an operation comes, it applies locally, then only it checks for consensus. If consensus fails, it will roll back to the original state. It was local first, but it could be intrusive. Can we envision an approach which is local first and non-intrusive, looking at the literature? Which brings us to the second research question, which is, can we design a consistency approach that can address our current limitations, which I just explained, while maintaining the Cheops local first, non-intrusive, and application agnostic principles? We took a step back into identifying the complete, the basics things about this consistency. So we observed two major patterns, which is operation-based consistency and state-based. In operation-based, consistency is based on an operation and synchronizing between the operations, and it could be application agnostic as it is done external to an application. Second one is state-based, in which consistency is based on an application state, and they could be specific to an application or a resource. So this gives us a clear higher potential for the operation-based consistency as our potential match. We observed two major operations for a stateful operations, which is iterative and replace. I'll explain this. So let's say in iterative operations, we have a positive negative counter in which the original value is c is equal to 5. We have an operation to increment the value by 10, and the value will be 15. Normal. Let's look at it in detail. We have an existing value, we have an operation, we have an argument, we get a result. If you observe closely, the result is dependent on the existing value completely. If the existing value changes, the other ones even if the argument is the same, the existing value changes, the value will be completely different. So we observe that in iterative operations, it depends on the existing value. Another one is replace operations, in which we again have a positive negative counter in which c is equal to 5 initially. We have a write operation, write 10. We get the value c is equal to 10. It overrides the value. Let's look at it in detail, which is, sorry for the temporary glitch. So we have the existing value, which is 5, and we override the value with 10. So here, if you see that the result is completely depend on the argument, which is 10. That is basically a replace operation. So it does not depend on the existing value. So let me remind our aim is to resolve the concurrent conflicts externally with respect to, we are following the Cheops principles. We have the iterative and replace operations. We combine it with the commutative properties to resolve two concurrent operations. We create 3 different classes to resolve the conflicts deterministically. Let's look in detail. Class 1 is called as iterative and commutative, which is we have a c is equal to 5, which is a positive negative counter with a initial value 5 replicated across 2 different sites. We have 2 operations which are concurrent, increment, decrement. So we apply it locally and then forwards it to the remote site. No issue, it's synchronized. Irrespective of the order, all replicas will converge. There is nothing big here, it's pretty simple, straightforward. Second one is class 2, which is replace and non-commutative, which is we have the same replicated positive negative counter with the value initial value c is equal to 5. We have 2 operations, which is write and decrement, which are concurrent. In such a scenario, we apply it locally initially at site 1 and site 2 where the operation happens, and we have a deterministic approach, something like, for example, a last writer wins, in which we only apply, we choose one operation based on a deterministic way which the user defined, and we choose only one operation to propagate. So here to apply. So here we have write 8, which is applied here, but we don't apply decrement here, which can ensure eventual consistency and the value being the same with both the sides. So applying a deterministic order can resolve such conflicts. The third one is iterative and non-commutative, which is we have 2 different concatenate operations which are concurrent. If we apply a class 1 solution, which is apply all, it fails, as mentioned here. Second one is class 2, which is last writer wins for deterministic order. It fails also, as described here, as shown here. So applying a direct solution fails in such a scenario, such that the operation cannot be converged eventually, especially because they are non-commutative. What we did in such a scenario is that we looked back into the literature, we saw the peritext algorithm. So peritext is a CRDT based algorithm, so by default they are intrusive. It relies on the commutative nature. We restructured this algorithm to make it non-intrusive with Cheops. For example, we have a string which is replicated across 2 different sites with the initial value high. We have to the same operation 2 concatenate operations which are concurrent. It applies locally first, sends to the remote sites, applies there. Conflict is detected by Cheops. Then what happens here is that we look at the deterministic order which is defined by the user, which is site 1 operations first, then site 2. Here what happens is that if we see the site 1, the order is already complete. Cheops can understand that. But on site 2, it is the other way around. So what Cheops does is that it rolls back to the original state, which is c is equal to high. Then it applies the operations in a deterministic order defined by the user, site 1, then site 2. And we are able to get an strong eventual consistency in which both of the replicas converge to the same value. Applying specific solutions such as peritext will solve the conflict. But is it generic and non-intrusive? So we analyze various solutions. For example, imagine that we have two concurrent operations in basic algebra with multiplication and addition, which are concurrent. It can never be converged. There is a recent solution which they have done with CRDT. Similarly, in concurrent edits in a collaborative text editors, like a Google Doc, like an Apple Notes, or any text editors, Shell LaTeX, for example. So these require specific algorithms such as auto merge, which is there in CRDT, Lagoot, even the decomposition of operations, for example, like that in CRDT. So what we do here is that such solutions we take and we propose something called as consistency logic, which is the DevOps can specify any consistency algorithm in a non-intrusive manner with Cheops, with this consistency logic. So let's say we have the same example. We propagate the operations, concurrent operations to the other side. When the conflict is detected by Cheops, what happens here is that it checks for the different operations which are there and it refers to the consistency logic which is already given by the user and it resolves the concurrency. So this is the basic workflow. We have some limitations, which is restricted API access. For example, in Kubernetes, there are some resources, for example, resource ID, which cannot be accessed via the API. For any application in such scenarios, if the API is not accessible, our current approach cannot work. Second one is strong eventual consistency versus correctness. Our approach aims for a strong eventual consistency in which we ensure that the value will be converged to the same value eventually. But it may not be the correct value. For example, in a banking scenario, which is two branches with the same bank account, they try to withdraw 100 euros concurrently from two different branches. They withdraw 100 euros. Sorry, initially the value is 100 euros. Then they concurrently try to withdraw 100 euros. It is successful as the operation is locally applied first. Then it gets propagated to the remote site. And when it reaches here, it will still be applied. But when they try to merge them, the problem here is that the current balance will become minus 100, which is a problem. So this is also existing in other approaches also. So this is a well-known problem in the literature. At the same time, even if we satisfy the consistency, we observe that the Cheops geo-distribution may fail sometimes. Let's take a look back into the Cheops basics, which is that we have two different applications, which are independent instances. Cheops tries to create an illusion of a single application by connecting them in a P2P manner among them. So the application directly are never connected within themselves. They are connected via the Cheops with each other to create a collaboration. So we ask the question, can this illusion be satisfied always? Here, let's take another example. We have site 1 in which we have a Dune audio. If a user requests to play this audio, the video at site 1, site 2, what happens here is that it will go to the site 2, but it won't work. The reason is that in the video streaming platform, we found that the audio could be strongly related to a particular video. So unless and until such a relation could be satisfied at the other side, an operation or a replication, for example, could fail. More concretely, we observed an example with Kubernetes. For example, if we try to replicate a pod A to site 2. So this should be the ideal scenario, but it fails. What we observed is that this particular pod A will have a strong relation with another resource, which is a secret K. So due to this strong relationship, unless this relationship is satisfied at site 2, this pod fails. So with such observations, can we ensure that the illusion of a single site can be satisfied, which is proposed via Cheops? Which brings us to the third research question. Can Cheops consistently maintain the illusion of a unified application across geo-distributed sites while adhering to the local first, non-intrusive and application agnostic features given by the Cheops principles? We focus on resource dependencies. The first step is to identify a dependency from relationships. A dependency is a relationship basically between resources that can influence or impact their life cycles. We identified 3 dependencies, which is a resource to resource, a resource to a service, a resource to its own environment. So let's look at an example for each. The same example in which the user tries to replicate a pod A to site 2. We already observed this example, and there will be a resource to resource. These are individual resources, independent resources, a relationship between these 2 resources. Unless and until this is satisfied, the request cannot be fulfilled. Second one is on an OpenStack application in which a user tries to replicate a VM called as P to site 2. In such a scenario, the VM needs to contact the service called as glance to get the image. But this particular image may not be available at site 2 to be to create the particular VM. So this creates a dependency between a resource and a service. The third one is a user tries to replicate, again in an OpenStack application, a VM called as K to site 2. Here what we observed, another observation which we made here is that the VM could have a very strong dependency to an IP within its own environment when they create the VM. So the IP, the same value, cannot be replicated between other individual instances of an OpenStack. This creates a dependency for a resource to its own environment. In many cases it could fail, in some cases it could be satisfied. So for all these types of dependencies which we identified, we have a solution which I won't be explaining in detail here due to the time limitations, but it is addressed in the thesis. And in order to, I'll just explain the core aspect of the solution, which is, in order to ensure the illusion works, what we propose here is another logic called as relationship logic, which is very similar to cross and consistency logic. And there are specific solution which is externalized for each dependencies which I just described with each of the types of dependencies. Let's say we have the same request going to Cheops. What Cheops does here is that it checks for the dependencies based on a predefined matrix or a DT given by the user, and it checks the relationship logic on how to solve or can we solve this relationship. And it will try to resolve the dependencies, then only it will forward the request. So once it resolves the dependency, then only the request is forwarded such that we ensure that the request can be satisfied. So I won't be explaining that further due to the time limitation. In conclusion, the initial question was, can we geo-distribute an application while being non-intrusive and agnostic? Yes, by externalizing some component from the application business logic for geo-distribution that are local first, collaborative then if required, consistency externalization, then the dependency management externalization. We added these components with the Cheops middleware, and we were able to geo-distribute an application in a non-intrusive and agnostic manner. In the future work and perspective, we have an proposal in this one to create automated error management with a MapK framework with control loops for each and every collaboration. Second one is addressing the limitation mentions for consistency and dependency, which is more clearly defined in the thesis. More importantly, my research here could be a step to reviving the aspect-oriented programming. Cheops showcases the potential for managing the cross-cutting concerns with the logics, with the individual logics, the cross logic, the relationship logic, and the consistency logic, in which we can separate the concerns from the application business logic in a geo-distributed system. And REST API could serve as a key entry to modularizing and handling these complexities. In my work, we published 2 different papers with my supervisor and my colleagues. And I have done international presentation with Open Infra Summit in 2022. I've done a few poster presentations in different summer schools, winter schools, and some workshops. And in the future, we have materials for 2 additional articles. One is for the consistency approach, one is for the dependency management approach. By this, I end my presentation. Thank you all.
Thank you, Geo. You perfectly managed the